Okay, this is lecture 19 on invariant maximality derivations by Harvey Friedman. Please.
Thank you. Okay, so this is the third. I had mentioned I was going to do three lectures on section 3.8. This is in chapter 3 on derivations. This is the heart, the main heart of chapter 3. Um, and there'll be some more lectures on chapter 3, the scope of which is a little bit unclear because I want to push this further into things I can do that are good and strong. I'm going to push this further until I can't, and then I'm going to mention some open questions next time. But today is just on finishing up section 3.8, and I'm going to go pretty fast. I'm going to go faster than normal because I'm going to cover things I've already covered before, but more polished and official, so to speak. So after I fool around with it a little bit more, like before Monday, I'll put on the downloadable manuscripts page uh, and a copy of this lecture, by the way. Uh, Downloadable manuscripts page, the whole of chapter 3 from 3.1 to 3.8 comprehensive. All right. So, uh, okay. So to review, this is chapter 3 of the book. I keep changing the title slightly. You might even not notice what I changed. It's called Invariant Maximality, Finite Free Choice, and Finite Games. The word free, I think, may not have been there before. And that's the title, and these are the actual section change. Section. This hasn't changed. These are the chapters. We're in chapter 3. We did this, a lot of lectures on this, and then we're finishing up on 3. This was done much earlier, I think, even last year. Um, there's been some polishing of that. Probably I'll have to say something about that. Then I really want to. This is important because this is the strictly finite form, and uh, there's going to be some nice, pleasant things going on here. All right. Uh, the table of contents has been changed slightly, changed only in 3.8 pretty much. The rest of the table of contents of the stuff we did is there. I'll emphasize in the introduction, by the way, it's important to know what somebody can skip when they read this chapter. Uh, uh, you notice that I had full usability and just plain old usability and all that stuff about plain usability could be omitted upon reading because of the fact that the highlights of this chapter are all connected with what's called full usability. That full usability just means that everything holds in every dimension. It's usable in every dimension K, and uh, we're using order constraints, the most general kind of constraint, order constraint. Okay. Uh, so this is what chapter 3, what the heart of 3.8 looks like. Uh, it starts with this being fully usable. That's because this is a finite function. It's covered. It's covered in all that work we did in section 3.6 on usability of finite functions. This is trivial. It's just a repeat. This is a nice, beautiful function. The simplest function I know of, well, I think almost provably the simplest function for which there's anything serious happening, anything really serious happening, uh, meaning well beyond RCA naught. I mean, this is kind of serious, but it doesn't involve the heart of the subject, which is to have parameters. Here, the parameters are in the interval, and I prove this using omega 1, and I prove this also. This is the whole thing, but I only have two usability. This is the whole thing, but I have only two usability. This is the whole thing that we're doing up here. But I only have two usability. I can get away with omega 1. Then we want to go to kappa. So this is uncluttered, not having to think about a cardinal kappa, just directly about omega 1. So somebody could, say, I want to get a little flavor of what possible set theoretic methods could possibly be relevant for such problems. They're well off just looking at 2 and 3. And then 1, of course, they've already looked at already, 2 and 3. Okay. So then we do this more general thing, so relative to an uncountable regular cardinal, and then we get the fruit of our labors, which is that I handle this function again fully k usable, k arbitrary, and I handle this function also k arbitrary. These are a little different. Here the gap is the gap is at 0, and here the gap is at 1. Here the gap is at 0, and here the gap is at 1. Now, in both cases, I use the same cardinal, namely, iterate the exponential cardinal function, like in Beth numbers, the minimum of k minus 2 and n minus 2 times, and then take the plus. And this comes out of Erdős-Radó. These numbers are important in Erdős-Radó theory, which is a large cardinal partition relation work, classical. And then, so you see what's happening is I set up a machinery. And then use it as a machine to convert large cardinal combinatorics, not necessarily large cardinal combinatorics. Cardinal combinatorics, like Erdős-Radó, for example, cardinal combinatorics into usability. So I set up a machine here that allows me to convert cardinal combinatorics into usability statements, which are implicitly pi 0, 1. Then I just look at the whole thing. Here's the whole thing. No, sorry. These two are related. I talked about this. Then I look at the whole thing, and I use a level of subtle cardinal, k greater than or equal to 3 and n greater than or equal to 2. If you don't have k greater than or equal to 3, if you have k less than or equal to 2, or n less than or equal to 1, then we're already backing stuff up here. So here I assume k is greater than or equal to 3 and n is greater than or equal to 2. And then I use this level of subtle cardinal, the min of k minus 2 and n minus 1. Then I just picked 3 very familiar formal systems and actually show and or remark, it's not really deep, show and or remark that these 3 are enough. Z3 is enough for the first 3. Z is enough for the next 2. And SRP plus is enough for the last 1. When I universally quantify over n. Okay. Now, I also, instead of using the formal systems, you can use the consistency of the formal systems plus WKL naught because the statements are implicitly pi 0, 1. That's pretty much automatic. That if you're implicitly pi 0, 1, you can convert proofs in a system to proofs in WK naught with con. assuming that the statement is implicitly pi 0, 1 over WKL naught, which is the usual. And in fact, here. We had earlier sections that proved that our usability statements, all of them, are uniformly implicitly pi 0, 1. There's a uniformity you can ask for also there, which is important. Okay. And I've left this vague. We'll really see what's going on probably. Well, next week, I'm going to bear down on what I want to put in here. Namely, more things are usable. More things are usable. More complicated things are usable. More general statements of what you can use. And then this is important technicality that if you insist that if you let the dimension be the n in here, then it doesn't change the statement. And universally quantify, then it doesn't change the statement. For all k and n, it turns out to be the same as for all n and n. And that justifies the statement we reversed. Because in the statement we reversed, k equals n. In chapter 4, k is equal to n. So we need to say this. We need to have this bookkeeping thing. It's elementary. All right, so now we're ready to do this. There's a lot of repetition, so I mean, I feel it's okay to go pretty fast through this and sketch, make some comments, but it'll all be in gory detail on the downloadable manuscripts by Monday, probably, even earlier, maybe. All right, so we've been through this before. This thing has already been done. That's fully usable. And that only used CIFA. It needed CIFA because it uses the Ramsey theorem for all exponents at once. Okay, so now we're going to do this one. This beautiful little one, we're going to prove this using omega 1, that this is fully usable. So I don't know how to prove it's fully usable in ZFC minus power set, but I have not tried a reversal, so I have to be a little careful. Probably I should spend some time trying to prove it in ZFC minus power set, just to make sure that, I mean, the best way to make sure that you can't prove it in ZFC minus power set is to do the reversal, right? But barring that, I got to be a little bit careful. But anyways, this proof is obviously using omega 1 seriously. So we have the spaces T alpha, alpha less than or equal to omega 1, a dense linear ordering less than star on T omega 1, and the well ordering less than double star on T omega 1, and the well ordering on T omega 1 to the K obtained by taking the K power exponent of this well order with the max lex. So first you order by less than double star, and then you order lexicographically. Okay. You canonically transfer any order invariant set downstairs is canonically transferred to T omega 1 KR, which is order invariant with respect to less than star, not less than double star, less than star. See, we're going to be high in the sky transfinitely with less than star, and we want to pull that down to the rationals from -1, 1, because that's where our statement lives. So we better make sure this is a dense linear ordering, which it is, with left and right endpoints. Then we make a greedy transfinite recursion on using less than double star. The obvious greedy transfinite recursion to come up with a set S of E, I call it, contained in T omega 1 to the K. See, the R is only used as a parameter in a general order constraint. The R doesn't appear here anymore. This is a K-dimensional set, which is uh, uh, it's going to be have maximality and invariance properties. And then we form countably many structures. We also form countably many structures. That's not what I meant. We also form the uncountable structures. I say it this way. T omega 1. T omega 1 has cardinality omega 1. So we form this structure, we add on the infrastructure, less than star, less than double star in the structure, and SE. Oh, I know, countably many. Okay, let me form the countably many, as I know what I meant, countably many uncountable structures. Yeah. And work with uncountable chains of countable elementary substructures. Yeah. So we build closed, unbounded, so to speak, substructures of this. Remember, this has a top point. You'll see this has, you recall this has a top point, omega 1 comma 0. We'll get into the details in a moment. But I say countably many because there are only countably many order invariant also order invariant E, or can also I'll do it this way, the countably many order invariant E. There are only countably many order invariant E. There are only finitely many order invariant E if I fix K and R. But in general, there's countably many if I fix K. Just what I'm going to do, the most relevant thing is to think of K as fixed. So there's infinitely many different R's you can use. But if you fix K and R, there are only finitely many of these. And we work with uncountable chains, okay, like in model theory, doing that kind of thing. All right. Let alpha be less than or equal to omega 1. So here's the definitions. T alpha is alpha cross 0, 1. This is the rationals between 0 and 1. Union this high point, just this high point. And then less than, now we're going to take kth powers. We're going to be using k tuples from here, so it gets more complicated. Because you can have this high guy and a bunch of low guys interspersed in a k tuple with some coordinates being on this top one and some not, you see. All right, less than star is the lexicographic ordering on T omega 1. We only need it on T omega 1. And that's given like this. Yeah. I meant to say, yeah, I meant to say that alpha 0. Oh, no, maybe it's covered. Yeah, if they're in T omega 1, yeah. So the highest one is going to be alpha 0. Omega 1, 0. So the highest point is omega 1 comma 0, the pair, yeah. We don't want to consider omega 1 comma a half. Okay. And then we have the restriction notation, just standard restriction. This notation. Okay. Now, we're going to define a second ordering, a less than double star. And for this, we have a fixed enumeration of, just a fixed 1, 1 enumeration of the rationals in here. But we have to start off with 0. It's important that we start off with 0. And then this is the linear ordering given by alpha less than beta, or alpha equals beta and I is less than J. See, this is quite different. This is like taking alpha across a copy of omega. See? Okay. And when you do this, this is just restriction notation again. When you do this, it's a well ordering, right? It's a well ordering. this less than double star is a well ordering, and it's just on the T omega 1. Oh, kappa, this is a mistake. Yeah, remnants from a previous version. This should be omega 1. So we extend less than double star to this by Maxlex, the usual way you would extend a well ordering to the kth Cartesian power of that well ordering. Okay, you don't have to read that. You know what it is. Less than star is a dense linear ordering with left endpoint 0, 0 and right endpoint omega 1, 0. It's not a well ordering. Less than double star is a well ordering with left endpoint 0, 0 and right endpoint omega 1, 0. Less than double star is a well ordering with left. I don't want to add more notation, so it'll be clear from context whether less than double star, what dimension less than double star is on. It's either on dimension 1 or it's on dimension k, where k is the number that is around. So don't worry about that. Left endpoint 0, 0 through 0, 0, and right endpoint omega 1, 0 through omega 1, 0. And this particular set, beta 0, is a closed set in less than double star with strict soup omega 1, 0. Yeah, so so that's the importance of this 0 being done right. In other words, in the enumeration, 0 is the first number. This is kind of important, that 0 is the first number in the enumeration that we use with the rationals. In that interval, left closed 0, right open 1, so that this is a closed set. Okay. So I have an order invariant set E. I want to transfer it to a transfinite one. So the transfer is sort of obvious. This is the canonical transfer if you have an order invariant relation, an order invariant set in some space, in some dimension, you can transfer it to a linearly ordered space. Then you can also transfer it to any other linearly ordered space with the same dimension in the obvious way. Okay. Let E be ordered invariant. S sub E. So this is the important construction. This is the greedy construction. Given E, I can go to SE, which is contained in T omega 1k. It's defined as follows. For every x in this space, k-dimensional space, x is in SE if and only if, when you tack it on, you're still restrained by E star. The rth power is constrained. Let's see. This is k-dimensional underneath, and when you raise it to the r, it's a kr dimensional set. So it makes sense that you care about whether it's contained in E star. So this is a constraint, and we now use E star as a constraint. Okay, this is the greedy defining relation. And S sub E is unique because it's a legitimate transfinite recursion. And also, we have a maximality built in. S sub E restricted to less than k double star x, this is that restriction notion, is maximal among the subsets of the set of all y such that y is double less than star x to the k, whose rth Cartesian power is a subset of ek star. Sometimes I like to use this language, whose rth Cartesian power. Sometimes this makes it easier to read. More English and a little extra English and less symbols goes a long way sometimes. All right, now we also have a set of ordinals that's very important. This is a set of ordinals for which you always have an elementary substructure. This is an important idea. See, we're going to look at elementary substructures whose domain looks like that. Okay, that's a mistake again. Omega 1 we're doing. Omega 1. Okay. so that this is an elementary substructure, and W exists and is a closed unbounded subset of omega 1 consisting of limit ordinals. And this is all uniform. In other words, this is over all possible E's. All right. The reason this holds, first of all, it stays closed because it's a countable intersection of closed sets. So we just need to show that it's closed unbounded sets. Needed to show it's closed unbounded for each E, And it's obviously closed because of model theory. A union of a chain of elementary substructures is an elementary substructure. And now it's obviously unbounded because you can actually make elementary substructures containing any countable amount of stuff by doing the Skolem-Hole construction. And how do you know that stays countable? It stays countable because omega 1 is regular. So use regularity of omega 1 in here. Okay. And this is an important collection of ordinals. And we let, okay. Omega 1. See, I originally wrote all this stuff with kappa, but I decided to isolate it to omega 1 because of the delicious usability that we're doing, namely 0, 1, semicolon 0, comma 1, and the other one with 2 usability. So that's why you see some kappas that weren't changed. Okay. Now we have the embedding that goes from T alpha to T beta, which is the identity on alpha cross 0, 1, which takes alpha to beta, so to speak. See, now we're going to do something like the Gödel collapsing lemma. This is what's really happening here. So we show that this is an isomorphism from here onto here. Now that's not obvious because in T of lambda alpha, the high point is alpha comma 0. So alpha 0 has to go to omega 1, 0. But alpha comma 0 has its own greedy requirements. Omega 1, 0, own greedy requirements that only refers to things below alpha. And omega 1, 0 has its own greedy requirements that refers to everything below omega 1. So you need to prove that this works. Okay, so the reason is, like in the Gödel collapsing thing, the reason is that this thing here satisfies that SE is the greedy set. This thing here satisfies that SE is the greedy, also satisfies that SE is the greedy set. Because in the case of alpha equals omega 1, in which this is a substructure, it was set up to be defined so that this is the greedy set. So the fact that this says this is the greedy set here means it's got to be part of the greedy set up here. So then that's why this works, you see. It's like the Gödel collapsing thing. When you collapse, you get a copy of, you get some mangled copy of L alpha after you do the transitive collapse, you see. So you L lambda, the lambda's limit order. So you got to know it's real L lambda if it's going to act like it. You see, it's the same idea, just more focused. All right, so let E be order invariant. alpha less than beta less than or equal to omega 1. Then pi is an isomorphism from here into here. So we don't have to keep talking about omega 1 anymore. It's just, we can look at just the countable ordinals and do this, right? And SE restricted to T of lambda alpha is maximal among the subsets whose Cartesian power is a subset of. And this is because of the fact that the greedy construction is maximal. And now we really have done the cardinal combinatorics we really want to do, which is really from omega 1 is regular, uncountable regular. And now we want to get it to, we can apply it to the subject at hand, invariant maximality. So we break this down. Here's a breakdown. If I let gamma 1, if I let a bunch of stuff be below lambda alpha 0, and this is one of the elements of the magic closed set W that we talked about. And I replace each lambda alpha 0. So there may be many alpha zeros in here, copies of lambda alpha 0 in here, because this is less than or equal, by lambda beta, a higher one, lift it, then I don't change membership in SE. Then I don't change membership in SE. And that's, of course, a step towards our usability, which involves replacing lots of different stuff by other stuff, by other higher stuff, and not changing membership. So we're on the right path. Okay, and also we have maximality. Maximality. Okay. So then we directly argue, I guess I didn't put the details down because I have too much stuff to cover here, but then you can easily get that this is fully usable. By taking a countable elementary substructure, you can get this. Just the idea is there's a way to go from this kind of thing to the real thing, which is straightforward. Okay. And then there's another one of these things that also just uses omega 1. So this one is like having two indiscernibles, so to speak, 0 and 1, an arbitrary dimension. But we saw that omega 1 is sufficient. Now here we allow any number of indiscernibles, but restrict the dimension to k equals 2. So in some sense, there's only two indiscernibles that can possibly be relevant because the dimension is so small. That's the idea. So since the dimension is 2, we only care about moving less or equal to 2 indiscernibles. We can already move one indiscernible by theorem 3846. Whoops, that's a 4. That sounds wrong. 2, 6. Right? That's what we did. We can move one indiscernible. We only have to address the moving of two indiscernibles, and omega 1 is sufficient. The reason is we can just use ordinary infinite Ramsey theorem to get to handle it. I actually you don't need omega 1 at this point. Omega, it doesn't make any difference. You can do what you did up here, but then cut it back further in order to handle two different indiscernibles. Because when you handle two indiscernibles in two dimensions, there are no parameters to worry about. So now you're just talking about regular Ramsey theory. You're just talking about regular Ramsey theory because there are no parameters. So that's why you can just use the regular infinite Ramsey theorem there. Okay. Now for this more powerful stuff, we have to wean ourselves off of the uncountable regular cardinal omega 1 and just use any kappa. And so we redo our machinery with hardly any change. but now we have to keep track of the parameter kappa. So this is just regurgitate. It's just the same thing. Just the same thing, just with kappa instead of omega 1. Yeah, so max Lex, this is all completely the same thing. Just for bookkeeping, the same bookkeeping is a dense linear ordering with left endpoint 0, 0, right endpoint kappa 0. It's not a well ordering. Less than kappa double star is a well ordering with left endpoint 0, 0, and right endpoint kappa 0. Less than kappa double star is a well ordering on T of kappa, kappa with left endpoint this, and right endpoint this, just as before, and this is closed. And we have E. See, this is really gentle. I could have done the general case of this first and just said that kappa equals omega 1, but I want to coax people into just focusing on omega 1. That's the idea. Because omega 1 is enough to do those really interesting little functions. Okay, so this is the lifting to the transfinite. So this is all the same. This is the same definition of greedy, so-called greedy condition. And again, no change, that it's unique. Everything's fine. And we define W kappa instead of W as this magic closed set. And we do this because this is a countable intersection of closed unbounded sets. A countable intersection of closed unbounded sets as before, because we're doing the elementary substructure now of this guy. Can we actually be better about this? Yes, there. And this is as you'd expect. And then we use this notation for the alpha element. And then we do this embedding thing, the same thing. We get the same thing because it satisfies greedy. We know that these embeddings actually do the right thing. They're actually isomorphisms. Maximality, the same thing. Now we do the lifting. This is again just the lifting of one indiscernible. We lift lambda alpha kappa 0 to lambda beta kappa 0, just the lifting of one. Okay. And it's maximal. So this is all the same. So now we apply it. Now the application of it is not that straightforward. See, a lot of the the complication involved here, and the reason I need this machinery this way is because otherwise I'm going to get a number that's too high. This does, I can move the indiscernibles, I can move indiscernibles using the large cardinal slave without much of this construction. Some of it is construction, but not all of it. I can do it, but I can do more. I can do one more because I have one for free. I have one lifting. I have a lifting of one for free I have a lifting of one for free because of this. See what I get? I have one for free, and that means that I get a better result. I would be off by one in this if I didn't do this. All right, so I'm going to get the full K usability using I'm going to iterate the exponential function the minimum of K minus 2 n minus 2 times. Now you might ask me what happens if K is 1 or n is 1? Then this doesn't make sense, or it doesn't exist, right? And that means I'm using nothing, but I ought to tell you what I'm using, and namely RCA naught would be enough. Because I'm either when n is 1, this is completely trivial. When n is 1, there's nothing to do. There's no motion, no invariance. But when K is 1, this is the old subject of dimension 1 usability, which which we went over before, which is easily handled, even for arbitrary function. Even for arbitrary functions, handled well, particularly if there are plenty of fixed points. Okay, so we proceed as follows. So we start with the Bagic. This is Erdős-Rado. Oh, no, no, no. I did, I'm sorry, I didn't state Erdős-Rado. I think that this is a problem. Just a second. No, I'm sorry. I'm sorry. This is Erdős-Rado. Let me start with the classical Erdős-Rado theorem. Yeah. So mu is an infinite cardinal, and let F map the n element subsets of x n minus 1 mu plus into mu. There exists a homogeneous set V of cardinality mu plus. Yeah. Okay, so x to the less than or equal to k is a set of tuples from x of non-zero length. F goes from kappa to less than or equal to k is order invariant if and only if it's constant on the order invariant sets. So we need a consequence of Erdős-Rado. We need to massage Erdős-Rado. Bit of a pain, but it can be done. So we have finally many functions from mu of dimension less than or equal to n, a whole bunch of these things, into mu, then I can get all these functions to be order invariant over a single set V of cardinality mu plus. Okay, and I give the gory details for this. You have to make up a bit of a complicated function and then apply Erdős-Rado to it by looking at order types and combining colors and so forth. Okay, so this is something that's easily handled, but it's a little messy to write down. We find ourselves using Eres-Radeau only weakly in the following sense. These homogeneous sets, we only really care that they're infinite. We don't really care that they're this big. We don't need it. Okay, now we have to define some, there's still some work to do to get this to be usable for usability. Work that we have to do that we didn't have to do in the case where we just used omega 1. We have more work to do here. Okay, so we have a pair AD. A has cardinality kappa. And A is a set of infinite orbitals of cardinality kappa, and D is a k-dimensional set. So this definition means that we can actually raise an individual indiscernible. The indiscernibles, the idea is the indiscernibles here are A. And we have kappa many of them. Namely that if I have a tuple with whose max is in A, is an indiscernible, and I raise the indiscernible to a greater element, then membership is the same. And remember, we basically proved that this was the case. If I have W sub kappa, comma, D, comma, SE, we're going to see that we already have for free this property because of all that infrastructure we did, that machinery. We already have this for a special A and a special D. We actually have this already. But we want to emphasize it as a general property called K special / little k, kappa special, sorry. Okay. And another special property. The definition of order equivalent mod omega. Order equivalent mod omega. You can imagine what this means. There's two tuples are order equivalent mod omega if they agree on their finite number, on their finite coordinates. And otherwise, they're just order equivalent. They're order equivalent and they agree at the finite coordinates. And order equivalent / omega over V means when two things in V union omega to the R, this is important, that's in V union omega. Two things in V union omega to the R, membership is identical. Okay, so this is a strong form of order invariance. And now we have a kind of a nasty to write down details theorem that if AD is exponential cardinal special, and it's with this K, then D is automatically order invariant sub omega over some infinite V. Okay. And if I didn't, okay, so this has to be done carefully, and that's actually a bit long. The ideas are clear enough, but it's a little complicated to write down, so I don't want to talk too much about it. But that completes the purely combinatorial development this year. Now, we actually have a slightly different space. We really need to consider the same thing when we just stick up. We have ordered pairs where we actually stick a rational as the second coordinate. We start with the adaptation of the definition of K special star K. So this is all trivial stuff. This just says that I can carry an inert second coordinate through the combinatorics. I can think of kappa cross singleton zero the same way I think of kappa. So there's really going to be nothing to this. This is all noise. And so we have the same statement here. And I put a star there to indicate that I've transferred it over to, instead of kappa cross, instead of kappa, I just have kappa cross rationals or kappa cross zero and so forth. It's just the same thing. So if you're special, then your order invariance slash, now instead of being order invariance slash omega, the analog of omega is singleton zero cross 0, 1, right? Because I'm multiplying by this. Yeah, sorry. Say in general, I'm multiplying by this set of rationals. So you get the same result. Okay, now from the infrastructure that we set up, the machinery, we already know that, and I already said this before, that this is already kappa special star K. This already allows for raising a single indiscernible to a higher one. Just one, though, just one. Now what I do is I unravel everything I said. As before, remember I unraveled when I was doing the thing for omega 1. Here I unravel this. But now I'm replacing all the elements of V cross singleton zero by their successors in here. Instead of just raising one, I can raise any number of them because of the large cardinal combinatorics we did. And then as before, this converts directly, easily to the full usability that we're interested in. Okay. Now, I claim I could use a smaller cardinal for here if n is smaller than k. For full usability, I can use a smaller n. In fact, I just use this one here, this cardinal. So if k is high up and n is down here, and I'm just looking at, 0 divided by n, or 1 divided by n all the way to n divided by n, then I can pretend that the large cardinal has to do with how many of these things there are, not the k. The dimension k doesn't make any difference. It's sort of like the way we did the thing with omega 1, because you can't use the higher dimensions because there's not enough stuff down here. So, and that's what reflected by this. You have to show, this needs to be proved. You have to show that you can get a set of indiscernibles of some decent size, no matter what the dimension is. You get a set of indiscernibles of size n from iterated exponentials of exponential length, n minus 1. This is a variant of the Erdos-Radeau theorem involving order invariance. It's not true if you don't have order invariance. Okay, so all right, so here uh, this is the key lemma about converting special to order invariance that we talked about earlier, except that it's pushed down. And I'm just talking about when the set of indiscernibles is of size n, but the k is huge. Yeah. See, because there's the k. There it is. There's the k. So that means that D has to be k-dimensional. D is k-dimensional. K is out of control, but n is, we're focusing on n, and I could just use this. So there's some tricky points that I can actually make be a cardinality n and not just n minus 1 and so forth. You just have to really look at it carefully. All right, here, um, this is the same thing as this, except omega is replaced by singleton 0 cross 0, 1. Yeah, this is the simple adaptation to the pure combinatorics to the particular kind of spaces we're involved with. Yeah, that's nothing. And then we break this down into exactly what we're saying. Again, you have to make sure that this is accurate. And just like before, we get this. This thing is we're replacing all of these indiscernibles by their successors. All right, and then we just get usability from here. See, this is very close to exactly what we want. We get the usability because we push it down into the rationals. We first make everything countable. Up here, things are not countable. They're transfinite. And we make it countable by taking a countable elementary equivalent substructure. That's how you get this. And then we have then we have this because we combine both of them together. The two statements together immediately imply this. In other words, you get min of k minus 2, n minus 2, because k minus 2 is good enough and n minus 2 is good enough. Because there are only n of these, you see. All right. Now, we talked about this before, but you also can do it for this when the gap is now the gap is at the end. The gap is between n minus 1 over n and 1. Before the gap was after 0, between 0 and 1 over n. And if you remember, what we did is we transferred the gap over to here. We first proved that we can move the gap, we can move this and we can remove the front of this entirely and remove the gap over here. That these are equivalent. We went over a proof last time, I believe, that those are equivalent. Their usability is the same. But of course, we haven't officially defined this monster because we've only defined it when the parameter set is in front. So it's just the same thing. You just go up by 1 here, up here. And then these are the parameters that are the identity. So we've just transferred the interval in the front to the interval in the back. And and we have equivalence. So we just have to worry about this new thing, usability. And you have to go through, which I do, you have to go through modifying the machinery to look at the different spaces. So we have to look at these different ordering. So the key point is this. Here's the key point. I'm not going to say much more because I am going to run over time some here. Instead of this, I'm sorry, instead of the interval from 0, 1, left close, right open, we use a fake, fictitious named interval 0, 1. We don't care that this is really 0, 1. All we need is it's an interval with left open, right closed that we stick at the end. Okay, but this one's left open, right closed. So we have to adjust these definitions. We adjust the definitions. The less than alpha it should be kappa actually. Because I only do it for that. Okay, that's done graphically, that's done geometrically. In other words, I really stick that over at the end. So that's done in a natural way. But here's the kicker. Less than alpha double star prime is supposed to be well ordering, remember? So we take the stuff at the end and put that in front when we do the well ordering. You see, there's a difference between less than star and less than double star in this context that we didn't have before, you see. That's why this can work. Okay, I'm not going to go through the details, but you can imagine, and you need to do that because you want to make this a well ordering. All right, so we go through this. I'm not going to spend too much time on this, but it is tricky that you have to set this up right. So we try to do everything as like we did before, and most of it just goes through standardly, but you just have to remember these definitions are changing a little bit. Basically, that stuff at the end is at the end with the dense ordering, but it's at the front with the well ordering. Okay, and we redo the structure with the elementary substructure stuff. There's nothing really too much changing, but you just have to remember what's happening here. And the pi is the same. The isomorphism stuff is the same. Maximality is the same. The definition of the greedy construction is the same, except with respect to, it has to be respect to this less than double star prime, which is a well ordering. And this is the raising of one, which is fine. All that's the same. And order equivalence, all this stuff is the same. And then we have to, so we have to go through and really rework everything for this. I don't know a good general way to do this without redoing it, which I do in the manuscript. So we got this familiar thing broken down, except instead of just zero cross that, it's that plus this. It's that inert set. That inert countable set plus, which takes the place of omega is now going to become like this, union this stuff at the end. The stuff that was at the beginning of the transfinite construction. And then we finally get to this. Exactly as before. Then remember we used the smaller cardinal and we needed to do this kind of stuff. All that goes through also well with this. So there's a lot of that also works for this. Okay, so then we get min. And then we also do this one. And this one is like the other one. Remember, we made this move before, changing the front, and we have to do this again. I'm sorry. We're done with all. I'm sorry. We're done with all the stuff that can be done in ZF, which is all doable and actually in Z. Sorry, we're done with that. I'm not going to repeat it. Here, now we're new topic. We actually do the whole thing. No gap. See, that runs all the way through. No gap. And we need a subtle cardinal of level min of k minus 2, n minus 1. The case when k is 2 or lower, and the case where n is 1 or lower, are in the first case, it was already handled with omega 1. In the second case, is trivial. So that's why we want this here. We just used this to clarify what we're doing. Okay, and this is its own thing with its own additional complications. And I'm not going to talk too much about it because I'm already over time. I'll just talk about some highlights. You use the same infrastructure.
Harvey, can we just
Yeah.
continue next time with this? Because
Okay. You got to go.
I have an appointment.
All right. Next week we'll finish this up, but I want to move on, and
Yes.
we'll finish this up, and take 15 minutes to finish this up. Okay. Thank you. We can end now.
Yeah. Okay.